Hi, I'm Colin Carter. I've taken a look at the chess problem from an information perspective and focused on the class diagram. I wouldn't claim to be a chess expert by any means. I gave up playing when my 10-year-old son could beat me every time. I tried to produce a class diagram using lots of class features because the purpose was to test the textual version of Bridgepoint. So let's take a look at the class diagram. So here's the class diagram overview, but we can zoom in and I can show you more detail. Okay, let's start over here. So we've got the game. Each instance of this will represent a different game. And each game involves a contest between two colors. So it's strictly a two rather than a one or many. It will only be two. And of course, that's white and black. And each color is played by a player. So we could capture the name of the player if we so desired. We come over this way a little bit, we can see that we've got pieces. So this is all the pieces. So each one has a color. So a color is associated with many pieces. So there'll be 16 white and 16 black. And each piece is of a type. And there are six instances of type for pawn, rook, bishop, knight, king, and queen. And we also have the square, so the 64 instances of square. And this association one captures piece in a square. So that's the current state of the game. Each piece that's in a square will have an association class instance capturing that. Notice that squares can be empty, so there can be squares with not occupied by any pieces, and pieces that are taken don't occupy a square, and the status is captured here. Note that the types haven't been sorted out in any nice tidy way yet. They're just either string or integer at the moment. They've not been tidied up as they would be in the final model. So that bit allows us to represent the current state of the game. But of course, what's interesting in a game of chess is what comes next. So how do we capture the potential moves coming up? Well, from a given state of the game, the Lichess server will give you a series of potential moves, possible moves, they call it in the class, which is this instance down here on the right. So for a given state of the game, you will get a set of those. And each possible move corresponds to one piece from one square to another. And a possible move brings about a new potential state of the game. So if you consider the starting position, from an initial starting position, there's a relatively small number of possible moves. Let's say it's 20. Each of those 20 moves sets up a different potential state of the game. And that potential state of the game is represented by this class here, which is the potential piece in a square. Now, after round one, the set of instances of this will be almost exactly the same as the instances of this, which was the state of the game at the start. So that represents, firstly, just one move on. So in fact, one piece will be different, all the others will stay the same. But of course, each move that's possible gives you a different instance of potential state of the game. So you have all of the corresponding states of the pieces for each state of the game. So if you could move 10 different pieces and you had 10 different potential states of the game, you would have a set of instances here, which represents where all the pieces are for each of those potential states of the game. So assuming you haven't taken anything, you'd have 160 instances of this. No, 320 instances of this, because it's 20 times 16 pieces. So that gives us a view of the potential places the pieces could be in for each of the possible moves. Notice that there's no attempt here to do anything about optimizing instance numbers. As you'll see, the instance population will grow quickly as we look ahead. Now, each potential state of the game, so if we've gone half a move ahead, we have a new potential state of the game, and there might be a whole bunch of them. Each of those would allow us to find out the set of possible moves for the next half move. So we can look forward by basically going, find the next potential state of the game, so one round on, then find the possible moves from that, generate the new set of potential moves, and it's effectively a tree structure that's going to grow here. And that's captured by this, the relationship between the potential states of the game by this one-to-many reflexive relationship down here. But of course, each time we go around that loop, the number of possible instances of these things is going to grow enormously, particularly when we're in the middle of the game where there's lots of potential moves and therefore lots of potential states of the game rolling out. But that's the basic notion of how you would capture the moves going forward in information terms. A couple of extra things that I included. One is a static set of data, which relates the piece types to the squares. In a bit of reading I've done on chess, then you see that some strategies take account of the square that the piece is in, because for example, a queen in a corner is less powerful than a queen in the middle. So this allows to capture the relative strength of a piece type in a particular place in the game. Just one of the things that can potentially enhance the evaluation strategy that you might take to consider. Of course, the purpose of an evaluation strategy is to come up with some numeric basis on which you pick the best potential state of the game for your next turn. And then when your opponent responds, you look at all the potentials again, and you would be throwing away instances as they become past and not possible and don't care instances anymore. So there would be part of the dynamics of this game would be to keep the instances cleaned up as possibilities disappeared. The other part of evaluation that I've hinted at, which was really to give me a supertype subtype class structure to try that out, is that there are various evaluation criteria that you can identify. I won't go into the details, and these are things I've come up with from my brief reading, but things like king safety, how easy it is for pieces to move, the structure of the pawns. A diagonal structure is more powerful than a straight line structure, and so on. So I haven't done anything with these other than put a placeholder there to say that you could enhance your evaluation criteria for each potential state of the game by considering all of these things. Okay, I think that's the gist of it. I will leave it to others to show you rather more dynamic versions of the chess game. So thank you very much.